This video series goes through the daily problems in this maths calendar that is published by the American Mathematical Society. You can either purchase it through their website or via Amazon. Today's question is to find the second smallest prime factor of 1,027,000. All we do is we test for divisibility by first 2, then 3, then 5, then 7, then 11, then a 13, etc., going through our prime numbers from smallest all the way up until we find the second smallest prime factor. Throughout, we will demonstrate some divisibility rules, even though of course we could simply take the number we're trying, perform the actual division and see whether or not there is a remainder. At the end, we'll also present some faster division rules and we'll also explain why they work. A number is divisible by 2 if and only if its last digit is even. Because 7 is odd, we know that 2 is not a prime factor. A number is divisible by 3 if the sum of its digits are divisible by 3. The sum of this number's digits are 1 plus 2 plus 7, which equals 10, which is not divisible by 3, so 3 is not a prime factor. 5 is also not a prime factor because the number does not end in a 0 or 5. One way to test for divisibility by 7 is using the following rule. It's actually better suited for smaller numbers, and at the end we'll present a faster way. We take the number we want to test and we split it into two parts. First we cross off the last digit and write down the remaining digits to get the number 100,002. Then we take the last digit and multiply it by 2. Then we subtract the former from the latter. In this case, we get 99,988. If this number is divisible by 7, then this number is divisible by 7 and conversely. So now we repeat the test on this number. We cross off the last digit to get 9998. Separately, we take the last digit and multiply it by 2. We subtract the former from the latter and we end up with 9,982. And we repeat. Cross off the last digit to get 998. Multiply the last digit by 2 and subtract the 2 to get 994. Repeat once again. Cross off the last digit to get 99, multiply the last digit by 2, subtract, we get 91, and if we wish, we can repeat one more time. We cross off the last digit to get 9, we multiply the last digit by 2, subtract to get 7. Because 7 is divisible by 7, our original number is also divisible by 7. Therefore, 7 is the smallest prime factor of this number. We are after the second smallest, so we need to keep going. To test for divisibility by 11, we are going to add, then subtract alternative digits. So we start with the first digit, which is a 1, then we subtract 0, add 0, subtract 0, add 0, subtract 2, add 7. We form this alternating sum of the digits. In this case we get 6. 6 is not divisible by 11, so therefore our original number is also not divisible by 11. For testing smaller numbers by divisibility by 13, we can do it the same way as for 7, except rather than multiply the last digit by 2, we multiply it by 4 and we add, not subtract. Specifically, we take our number, cross off the last digit to get 100,002. We multiply the last digit by 4, we add, we get this number, we repeat the process. We ultimately end up with the number 46. Since 13 does not go into 46, 13 also does not go into our original number, so that's a no again. Same thing for testing by 17, except this time we add 5 times the last digit. and we end up with the number 56, which is not divisible by 17, so 17 also fails. For divisibility by 19, rather than do it the slow way, which is essentially similar to what we've done before, where we cross off the last digit, look at the number out the front, and then for 19, we multiply the last digit by 2 and add. Rather than do that the whole way through, we start off with a different rule which will allow us to reduce the size of the number faster. Precisely, we're going to add 4 times the last 2 digits to the number out the front. So cross off the last 2 digits, we're left with 10,000. We add to that 4 times the last 2 digits to get this number. We repeat, cross off the last 2 digits to get 101. Add to that 4 times the last 2 digits, which in this case is just 8, to get this number here. And now we switch to a rule that involves just crossing off the last digit. So from 133, we cross off the last digit to get 13. We multiply the last digit by 2. We add to get 19. And 19 is divisible by 19, so our original number is also divisible by 19, and therefore 19 is the second smallest prime factor of 1,027,000. There is a faster divisibility rule by 7 for numbers that have got 5 or more digits. Given a number, we break it up into groups of 3 digits starting from the right-hand side. So in our case, we have 3 groups, 1, 000, and 027. We form an alternating sum, so we have 1 minus 0 plus 27 gives us 28. Since 28 is divisible by 7, so is our original number. The same procedure works for divisibility by 13. Take our number, break it up into groups of 3 digits starting from the right-hand side, form the alternating sum to get 28, and our original number is divisible by 13 if and only if this number is divisible by 13. Since 28 is not divisible by 13, our original number is also not divisible by 13. Divisibility by 17 can also be tested by leaving off the last 2 digits. So we leave off the last 2 digits. This time, whatever remaining number we get, we multiply it by 2. So we leave off 27, we get 10,000. We multiply 10,000 by 2. Then we subtract off the last 2 digits, in this case 27, to get this number. Then we can repeat, cross off the last 2 digits to get 199, multiply it by 2, subtract off the last 2 digits to get this number. And one more time, we leave off the last 2 digits to get 3, we multiply it by 2, and then we subtract off the last 2 digits. I flipped this around because otherwise we would get a negative number, but that doesn't matter. Negative 19 is divisible by 17 if and only if 19 is divisible by 17. Our original number is divisible by 17 if and only if our final number here is divisible by 17. Since 19 is not divisible by 17, then we know our original number is not divisible by 17. To explain why these division rules work, we need to introduce the idea of modulo arithmetic, also known as clock arithmetic. If we work modulo 12, then we can think like the hands on a clock. 5 mod 12 is just 5. 13 mod 12, if on the clock you're at 12, and then you add 1 more hour, you arrive at 1. 60 mod 12, you can think of this as going around the clock 5 times. 5 times 12 is 60, so you arrive back at 12, which is also the same as 0. Indeed, modulo 12, we want to get a number between 0 and 11, rather than between 1 and 12 on an actual clock. 63 mod 12 is therefore 3, because 5 12s are 60. We subtract off 60, we have 3 left over. And indeed, whenever we go round the clock face, it's equivalent to just subtracting or adding 12 to the number here. Mathematically, to compute what a number is modulo 12, we just keep adding or subtracting 12 from the number until we reach a number between 0 and 11 inclusive. So for 13, we just have to subtract 12 once to get 1. For negative 2, we just have to add 12 once to get 10, and so forth. Note that a number is divisible by 12 if and only if that number, modulo 12, is equal to 0. A key property of modulo is that x times y modulo 12 is the same as x modulo 12, all multiplied by y modulo 12. So for example, 15 times 25 modulo 12, we can work this out the slow way by first doing 15 times 25 to get 375. Then we write 375 as 31 times 12 plus 3, which shows that the answer is 3 modulo 12. The fast way though is to use this rule here. We first compute 15 modulo 12, then we compute 25 modulo 12, then we multiply the answers. 15 modulo 12 is 3, 25 modulo 12 is 1, 3 times 1 is 3. Of course, we can work with modulo any other number. There is nothing special about 12, except we have 12 hours on a clock face, and this rule works regardless of the modulo we are using. One of the rules we used to test for divisibility by 13 involved breaking the number up into groups of 3 digits. We will show how it works for 3 groups of 3 digits here. Such a number can be represented as 1,000,000 times x plus 1,000 times y plus z. So if x equals 123, y equals 456, and z equals 789, then this recovers our original number here. We want to know if this number, modulo 13, is equal to 0. So we're interested in taking this number and performing modulo 13 on it. Using the previous property, we can perform modulo 13 on each of the coefficients here. 1,000,000 is equal to 76,923 times 13 plus 1. So 1,000,000 modulo 13 is 1. 1,000 modulo 13 is 12, or equivalently negative 1. So we can write here negative 1 times y. And z has the coefficient of 1, so it just stays the same here. So what we've shown is that computing what our original number is modulo 13 is the same as computing what x minus y plus z is modulo 13. So in particular, this number is divisible by 13 if and only if this number is divisible by 13, because a number is divisible by 13 if and only if modulo 13 it equals 0. When we tested for divisibility by 17, we separated out all the leading digits from the last 2 digits. So that's equivalent to writing our original number as 100 times x plus y, where y is the last 2 digits and x are all the digits in front of the last 2 digits. We're interested in what this number is modulo 17. Our number is divisible by 17 if and only if modulo 17 it equals 0. Taking modulo 17 of the coefficients, 100 modulo 17 is 15, so this is equivalent to 15x plus y modulo 17. 15 modulo 17 is the same as negative 2 modulo 17. 15 minus 17 equals negative 2. So we see that if negative 2x plus y modulo 17 equals 0, in other words, if negative 2x plus y is divisible by 17, then our original number is divisible by 17. And since a number modulo 17 is 0 if and only if its negative is also equal to 0 modulo 17, we're free to choose either y minus 2x or 2x minus y in here. Whichever one gives us a positive number would be more convenient.